Here's something that might blow your mind. The coffee cup on your desk right now is actually behaving like a wave, just like light or sound. You can't see it, but according to quantum mechanics, everything around you, from your smartphone to your car, exists in a strange wave-like state that defies our everyday experience. But here's where it gets controversial. Most physicists have simply accepted that this quantum weirdness magically disappears when objects get big enough. They've drawn an invisible line between the tiny quantum world of atoms and our familiar classical world of everyday objects. What if that line isn't as solid as we thought? A groundbreaking team of researchers from Switzerland's ETH Zürich and Spain's Institute of Photonic Sciences in Barcelona just shattered some long-held assumptions about this quantum classical boundary. They've managed to extend the mysterious wave-like behavior of objects that are 1,000 times larger than atoms. And this achievement could revolutionize everything from fundamental physics to ultra-sensitive gravity sensors. Let me break down what they discovered and why it matters to anyone curious about the true nature of reality. The quantum world operates by rules that seem absolutely bonkers compared to our daily experience. While you can pinpoint exactly where your car keys are, hopefully, an electron doesn't have a definite location until someone measures it. Instead, it exists as a probability wave spread out across space. The million-dollar question that's puzzled physicists for decades is this: why don't large objects like tennis balls or buildings exhibit this same bizarre behavior? The answer lies in something called coherence length. Think of it as the spatial reach of an object's quantum wave nature. For large objects, this coherence length is incredibly tiny, far smaller than the object itself, which makes quantum effects practically invisible. It's like trying to see ocean waves through a microscope. They're there, but the scale makes them undetectable. And this is the part most people miss. To bring quantum mechanics into our macroscopic world, scientists need to simultaneously increase both the size of objects and their coherence length. It's like trying to inflate a balloon while also stretching it. Incredibly challenging, but not impossible. Lead researcher Massimiliano Rossi and his team tackled this challenge using silica nanoparticles that measure 100 nanometers in diameter. To put this in perspective, these particles are still invisibly small to our eyes, but they're absolutely massive compared to individual atoms. The researchers essentially turned these nanoparticles into quantum performers, making them dance to quantum rules rather than classical ones. Their experimental setup reads like science fiction made real. They trapped these nanoparticles in mid-air using nothing but focused laser light, creating an invisible cage in a vacuum chamber. Think of it as the most sophisticated optical tweezers you can imagine, holding particles smaller than viruses suspended in empty space. Here's where the real magic happens. When the nanoparticles naturally scatter the laser light, the scattered photons carry encrypted information about the particle's exact position. The cold particles, on the other hand, settle into pure quantum states where their wave-like nature can extend much farther in space. The team initially measured a coherence length of 21 picometers. That's 21 trillionths of a meter. Incredibly small, but measurable. But here's where it gets controversial. The researchers didn't stop there. They performed what can only be described as quantum acrobatics with laser light to push these limits even further. Using high-power laser light, they created what physicists call a harmonic potential. Imagine a marble trapped at the bottom of a steep-sided bowl. The beauty of using light-based traps is their incredible tunability. Adjusting the laser power is like reshaping the bowl from steep to shallow with surgical precision. The team then executed a carefully choreographed sequence, reducing the laser power in 2 calculated pulses. Each pulse made the bowl shallower, allowing the marble, our nanoparticle, to explore a larger area. In quantum terms, this translated to expanding the particle's coherence length to an impressive 73 picometers, more than tripling the initial measurement. You might be thinking, 73 picometers still sounds impossibly small compared to the 100 nanometer particle. You're absolutely right. And that's exactly what makes this achievement so remarkable. The researchers have demonstrated that there's no fundamental barrier preventing them from pushing this boundary even further. But here's the catch that keeps physicists up at night. A process called decoherence constantly works to destroy quantum information. Rossi explains it perfectly. When a nanoparticle interacts with its environment, it becomes entangled with the noisy, chaotic world around it. This interaction gradually erases the particle's quantum signature, turning it from a mysterious quantum wave back into a boring classical ball. Imagine trying to maintain a perfect sandcastle while waves constantly crash against it. That's essentially what these researchers accomplished. They built quantum coherence faster than the environment could tear it down. They meticulously identified and eliminated every source of interference, with laser light scattering being their biggest nemesis. The implications of this work extend far beyond academic curiosity. These techniques could lead to revolutionary gravitational sensors capable of detecting the tiniest space-time ripples, potentially opening new windows into cosmic phenomena we've never been able to observe directly. Rossi himself acknowledges that while 73 picometers might seem modest, there's no known fundamental reason why nanometer-scale coherence lengths should be impossible. Think about that for a moment. We might be on the verge of creating quantum objects visible under powerful microscopes. The next frontier involves using hybrid traps that combine both light and electric fields to confine nanoparticles. Electric traps could dramatically reduce decoherence from light scattering, potentially allowing for much longer expansion times and correspondingly larger coherence lengths. Rossi is already pursuing this direction in his new research group at Delft University of Technology. This research challenges one of the most fundamental assumptions in physics, that quantum mechanics and classical mechanics operate in completely separate realms. What if the boundary between these worlds is more fluid than we ever imagined? Here's a thought-provoking question for you. If researchers can eventually create quantum coherence in objects large enough to see with the naked eye, how might this change our understanding of reality itself? Could we one day witness the strange quantum behavior of everyday objects directly? The journey from 21 to 73 picometers might seem like a small step, but it represents a giant leap toward answering one of physics' most profound questions. Where does the quantum world end and the classical world begin? And perhaps more controversially, does that boundary even exist at all? What do you think? Are we approaching a revolution in our understanding of reality, or will classical physics always dominate the macroscopic world? The answer might reshape everything we think we know about the universe around us.